Okay, we're going. Last time we looked at Coulomb's law, and I wanted to work through an example where you use Coulomb's law to actually find the electric field. So I think we talked about charge distributions, line distribution, surface distribution, volume distribution. In this example, I want to find the electric field due to an infinite line charge of density rho L along the z-axis. So it's always helpful to have a picture. So this is an infinite line of charge. The charge at any length L segment would be rho L times L. Rho L has units of coulombs per length, coulombs per meter. So now the question is, and we can evaluate Coulomb's law in any coordinate system. We want to find the electric field in an arbitrary point R located anywhere in three-dimensional space. So the first thing to think about is, which coordinate system. Cylindrical is the right choice here. And if you can think about this infinite line charge, when you're looking toward that line charge, there's no dependence on the angle, the rotational angle. There's no dependence on z. Remember, it's infinitely long, so no matter how far up you are, when you look up, you're still going to see an infinite line. So although you can evaluate this using any coordinate system, it will be simpler to use cylindrical coordinates. Now, what we'll look at in just a bit is Gauss's law. And in Gauss's law, we can use it to more simply find the electric field than using Coulomb's law. Coulomb's law is actually a special case of Gauss's law. But usually when you apply Coulomb's law and its what's called its integral form to find the field, you have to take advantage of these symmetries and recognize these in the field itself. So in this coordinate system, we can represent an arbitrary point as it's rho in the rho direction, which is radially out. So this is our vector R. We also need a vector to a point in our charge distribution. So again, here it's a line. So an arbitrary point here, this is our prime vector. It's a vector to a point within the charge distribution. So again, could be a sphere, could be a point, could be a line, could be a surface. Now, because it's restricted to a point along the z-axis, this r prime is just z. And here we need to introduce this new coordinate z prime, which is the distance from the origin to this point in our charge distribution. Z is this height above the xy plane to an arbitrary point at which we're trying to find the field. So we've got these two vectors. R points anywhere in three-dimensional space. R prime is restricted to a point on our line distribution. So, but Coulomb's law in this case, at least setting it up, is quite simple. You know, evaluating it's the hard part. So this is the electric field at any point R, and Coulomb's law says, at least for this line distribution, it is, let's see, R minus, I'll write down the full thing first, R minus R prime over the magnitude of R minus R prime cubed, rho L, and then DL, but our DL is DZ here. Okay. In a general case, it was an integration along the contour. So this is Coulomb's law for a line charge. The only difference for a surface charge is this becomes rho S, and this we integrate over a surface. Or if it's a volume distribution, this becomes rho V, and it's an integral over the volume, a triple integral. So substituting in infinity of R minus R prime, we have rho hat, rho, and then we'll have plus Z hat, Z minus Z prime. Actually, let me back up here. This should be DZ prime, okay, because I'm integrating along my line, and the coordinates I'm using along my line are there. This is this Z prime. And then in the denominator, the magnitude of rho hat, rho plus Z hat, Z minus Z prime, magnitude cubed. I'll pull out the rho L here because it's a constant along this line. It's not always the case. Rho L can actually be a function of Z prime, for example. But in this particular case, it's a constant line density. Now we need to attack this magnitude, rho hat, rho plus Z hat, Z minus Z prime cubed. The magnitude of the vector is the square root of the sum of the squares. So we have the square root of the sum of the squares to the third power. So this would become rho squared plus Z minus Z prime squared, now to the 3/2 power, because the magnitude is to the 1/2 power, and then that's to the third power. So now we have for the electric field at any point, rho L 4 pi epsilon, integral from minus infinity to infinity. I have rho hat, rho plus Z hat, Z minus Z prime, all over rho squared plus Z minus Z prime squared to the 3/2 dZ prime. Now, the next step is actually to break up the numerator. So we get a little closer. Remember, this is a vector. By rewriting this as rho L 4 pi epsilon, and then now I'm going to break the numerator up, so I'll have a rho hat component, integral of minus infinity to infinity of rho squared plus Z minus Z prime squared to the 3/2 dZ prime. And then I'll have the Z hat component, minus infinity to infinity, Z minus Z hat, rho squared plus Z minus z hat squared all to the 3 halves dz prime. So now we've got an expression for the electric field at any point in space. I need to try and evaluate these integrals. Granted, they are nasty looking. They simplify it a little bit. If we let lambda equal z prime minus z, then d lambda is equal to dz prime. And we get rho L 4 pi epsilon rho hat as z prime goes from minus infinity to infinity, lambda will go from minus infinity to infinity. So it's just an integral substitution. This is rho squared plus, now this becomes lambda squared to the 3 halves d lambda. And the second one becomes lambda over rho squared plus lambda squared to the 3 halves d lambda. Now, I mean, you can remember back to calculus 2, I think we did these trigonometric substitutions if you want to evaluate the integral and go through that, or look it up in a handbook, or go to Wolfram Alpha or Maxima or whatever to evaluate these integrals. This one is actually 0 because it's odd. We're integrating from minus infinity to infinity. But notice at, say, minus 1, it's going to be the negative of what it is at plus 1. So whatever this thing is, due to the lambda in the numerator, it's odd, and so we're integrating over this odd function over a symmetric integral around lambda equal to 0. So this is just 0. There is no z component. And you could actually even tell that kind of from the symmetry of the problem, that there couldn't be a z component, because no matter where we are in z space, we see the same picture. Okay? We see this infinite line. Now, fortunately, this one evaluates 2. Let me pull out the rho hat. We'll have rho L 4 pi epsilon. It evaluates pretty simply to just 2 over rho. And so I get rho hat, finally, rho L over 2 pi epsilon rho is the final result. Now I've got a lot of rho's floating around here. I've got rho hat, which is this unit vector directed radially outward from my z-axis. I've got rho L, which is something completely different, right? That's the density, the charge density along this line in coulombs per meter. And then I have in the denominator rho, which is the distance to the point. So we see, at least for this infinite line charge, as I get farther away from the charge, the field gets weaker by 1 over rho. As opposed to a point charge, the field gets weaker as 1 over r squared. But this is a classic problem in electromagnetics, finding the electric field due to this infinite line charge. There are a couple of other classic problems. One is an infinite surface charge. Now, do we ever have the case where we have an infinite line charge? No, not in real life, or an infinite surface charge? No, not in real life. But if you are dealing with a very long line charge and you're near the center, the field should be approximately what you get from making this assumption that it's infinitely long. If you can actually work the problem using Coulomb's law if the line charge is finite length. But then it will have a z component, because as you move around in z space, you know, you can see the line, you can see yourself get farther and farther away from this line segment. That becomes even a more difficult problem to work out. It's set up pretty much like this, but in this case, this integral goes from, you know, minus L/2 to L/2, for example, on both of those. And actually that this other integral doesn't disappear. You have a z component to the field. Now, so there are a couple of additional examples like this in the book. One where he does the infinite plane. I think in one of the homework problems, you're asked to find the field due to an infinite line and an infinite plane of charge. So you don't have to start that over from scratch, just use superposition. This is the field due to the line charge, and in the book, you've got the field due to a surface and then the surface. I think in the surface, actually let me pull that up from the book. So he works, he's got a couple of classical cases. One, what's the electric field due to a ring of charge? Okay, so again, cylindrical coordinates are the right there, and then this is the answer he gets. It does depend on the height at which you are above or below the ring. Now notice here that the z in the numerator means that if you're above the ring, the field is going to be pointed in the positive z direction. Well, this is not the general expression for the field. This is just the field along that line. So it's not for an arbitrary point, but for the field along the z-axis. So he uses the symmetry to actually simplify the problem. And here's another one where we have a picture. Did I skip over the picture? Because he doesn't have the picture. It's on the next page. Maybe. So this is a solid disk of charge. Here again, he's finding just the field along the z-axis and gets this result. Now this signum of z is just the sign of z. So it's either plus or minus 1. It's plus 1 if z is positive. It's minus 1 if z is negative. Now, in the case where the disk becomes infinitely large or has an infinite radius, then it's true in general, okay? Because then there is no really z-axis. Any point, you know, if the field of charge is infinite, no matter where you are above, you should see the same field. And he has that case here, and it reduces quite simply to just this result when you have an infinite plane of charge. So it doesn't depend on the distance at all, which is kind of surprising. It doesn't matter how far away you are. And that's kind of one of these peculiarities when you're dealing with infinites. It's an infinite plane of charge, so no matter how far you get above the surface, the field intensity is the same. It only depends on the sign. And again, the sign here is just a little artifact that if you're above, it's actually taking care of the direction of the unit vector. If you're above, this is plus 1, and the field is directed upward. If you're below the plane of charge, it's just directed downward. That's all the signum of or sign of z. But it has constant field strength, rho s over 2 epsilon. So, you know, in the homework, I think that you probably have one problem where, you know, it has you to attack a problem using Coulomb's law. It usually leads to some, unfortunately, nasty integrals. what I'm looking for primarily is that you set the problem up correctly. You get these expressions for the field. Feel free to use a handbook, some Wolfram Alpha to evaluate the intervals. I don't expect you to do that, but set up the problem correctly. What we're going to be looking at now is some easier ways to actually solve for the electric field. And Gauss's law is one such method. Okay, Coulomb's law is actually a special case of Gauss's law. Gauss's law is one of four fundamental equations fundamental to electromagnetics. They're known as Maxwell's equations. So Gauss's law is one of Maxwell's equations. It's pretty simple, actually. It says, remember this integral d dot ds, and this is to a closed surface. This is the net flux of the D field, which is our electric flux density. Okay. So flux density times area gives us flux. But Gauss's law says the net flux density through any closed surface is equal to the charge enclosed by that surface. It's pretty simple. There's another form of Gauss's law that we'll talk about. It's not obvious how we actually use this to solve for D. D is the electric flux density. It's really useful only when we have certain symmetries that we can take advantage of to solve for the D field. But when it can be used, it leads to results more simply than Coulomb's law. So electric field of a point charge. Now we've seen this already, but let's see if we can get this from Gauss's law. So I'm going to have a point charge Q here at the origin. Now, this doesn't have to be a physical surface that we're talking about. It can be just a virtual surface, any surface that we can, just a surface defined in three-dimensional space. Now, what we're going to use here for our surface is actually just a sphere. Okay. Now, why? And based on the symmetry here with Q, a point charge, that we know the field can't be dependent on phi, our rotational angle around the xy plane, right? Because when we look toward the charge, no matter if we're an observer standing at some angle phi, if we look toward this charge, we see the same charge. We see this little sphere of charge at the origin. Likewise, with regard to the theta, as you rotate around the thing, you see the same picture looking toward the charge. And you have to recognize those symmetries in order to be able to use Gauss's law to find the D field. So it's not, you can't always use it. But in this case, I can make the argument that the D field can only have a component that depends on R. That's R directed, can't be phi directed, can't be theta directed. This is in spherical coordinates. It may be a function of R here. So dr is not a constant. It may be a function of R. Back to the line charge over here, I do cylindrical coordinates, and by this argument, I can make the argument that D is just has a rho component. Okay? Can't depend on Z. For an infinite line charge, can't depend on phi. And so we could get to this result a little more quickly in using Gauss's law, but in order to use it in its integral form like this, you have to be able to recognize these symmetries and simplify the problem. Okay. So I'm going to choose a sphere of radius r as the enclosing surface. And then, on your handout for, a little surface element here on the surface of the sphere, this little patch here, there is no r component to that area, but there are d phi and d theta components. It's directed radially outward. Remember, that's a normal, and then our direction is outward from our enclosing surface. That's the assumption here in Gauss's law. And then the area does depend on the radius. It's r squared sine theta d phi d theta. Again, that's on your handout. You've got that handout to give you all these surface areas for, in the different coordinate systems. So integral of s ds becomes, in this case, well, carrying out the dot product, r hat, that's 1. So we get dr r squared sine theta d phi d theta. D phi goes from 0 to 2 pi, and theta goes from 0 to pi. Now, dr can depend on r, but we know it doesn't have a phi or theta component. So we can pull it out of the integral r squared as well. Okay, so this actually becomes dr, d subscript r squared. Integrating over phi from 0 to 2 pi gives us 2 pi. We integrate sine theta from 0 to pi, we actually get 2. So this becomes 4 pi dr r squared. For the net flux of the d field. So there is a net flux. Now, if there were no charge here, the net flux would be 0. That's the other thing Gauss's law says, that in order to have a net flux through any surface, there has to be charge inside the surface. Now it's net flux. We can't have the same flux going through the surface as we have exiting it. So there can be a d field present even when there's no charge enclosed in the surface, but there's just no net flux created unless there's a charge. I'll talk a little bit more about that in just a second. We also, now, this is the left-hand side of Gauss's law. We have that this has to be equal to 4 pi r squared dr, has to be equal to the charge enclosed. In this case, I called that Q. So this leads to dr is Q over 4 pi r squared. And then now going back to d, so d has to be r hat Q over 4 pi r squared. And then if you remember the relationship between our E field, our electric field intensity, and our electric flux density, they just differ by epsilon. So we get E is r hat Q over 4 pi epsilon r squared as our result for the E field in this case. Okay, which we've seen that before. That's the electric field of a point charge. We actually got that from Coulomb's law. I'll do one more example here. Field of infinite line charge. This is the same problem we worked at the beginning of the period. Okay, but now there we use Coulomb's law, but now we're going to use Gauss's law. It's infinitely long. Okay, but I'm going to choose as my surface just a cylinder enclosing a portion of the line. Gauss's law applies for any shape. I'm going to say it has length L, goes from minus L over 2 to L over 2. And the cylinder has a radius of A. Now, due to symmetry now, I'm going to argue that the D field can't have a phi component. It can't have a Z component because it's an infinitely long line of charge. But it can have a rho component. So you have to recognize that in order to take advantage of Gauss's law. So choosing this cylinder, choosing an appropriate shape is also important. The charge enclosed here, remember this has a density of rho L. So the charge enclosed here, since rho L is constant, it's just rho L at the times the length of the line segment. Rho L, L. Or we're integrating a constant from minus L over 2 to plus L over 2. So the charge enclosed in this surface is rho L, L. The ds component here, we've actually got to, let me back up. Consider d dot ds. Now remember, this is always a closed surface. So I not only have the sides of the cylinder, I have the tops and bottoms. But on the top and bottom, ds is plus or minus z hat rho d phi d rho. This is a little element here on the top. On the top, it's going to be pointing in the plus c direction. But on the bottom, since it always points away from the surface, it would be pointing in the minus c direction. So on the top, it's plus. On the bottom, it's minus. I'm just combining them both. Okay, but we've made this argument based on symmetry that D is just radially directed. So that dot product is going to be 0 on the top and bottom. They're at 90 degrees. So on the top and bottom, d dot ds is equal to 0. To be considered. Now on the side, ds is rho hat a d phi dz. Again, that's on your handout for the surface element on the side of the cylinder and cylindrical component and cylindrical coordinates. And so now on this side, now my notation here, I'm not including the circle because I'm just doing on the side of the cylinder. Now in this case, since the contribution from the top and bottom is 0, this would be equal to the net flux. But here, it's a surface integral now, so it's going to be a double integral. This dot product gives me A, D, rho, and then I have d phi, dz. I'm integrating over rho from 0 to 2 pi, and dz from minus L over 2 to L over 2. So I can pull the A, D rho out. So this is just an integral over constants. And I get 2 pi L, A, D rho. Or d rho is from Coulomb's law, from Gauss's law. Two pi L A D rho. This is the net flux, is equal to the charge enclosed, is rho L L. So the L's go away. I get d rho is rho L over 2 pi A, or D is rho hat rho L 2 pi A. Now this is the field along the cylinder of radius A. Again, it's a virtual cylinder. And more generally, for a cylinder of radius R, I can generalize this more generally. At any point, it's rho L over 2 pi R, and E is rho hat rho L over 2 pi epsilon R, which should be the same result I have way over here, you know, that I got from Coulomb's law, trying to evaluate these nasty integrals. But here, using Gauss's law and again some symmetry, I get the same result much more simply. I won't say it's easy, but it is simpler than Coulomb's law. Now, unfortunately, Gauss's law is not I can't always use it to find the field. The problem with it is, here, you know, I'm giving you the result of an integral. It's like me telling you, we integrate over something and get the result 10. Okay, what's the something? What's the integrand? Okay, that's really the question. You know, I tell you that we integrate something and we get 10. You have no idea what that something inside is, usually, right? It could be integrating 1 from 1 to 10. It could be integrating like the absolute value of a sign. Really could be anything, you know, x squared over some interval. So that's the basic problem. You can't use Gauss's law to determine the D field or the E field except in these highly symmetric situations. Okay, when there's this symmetry involved and we can make these arguments about the form of the D field, then we can carry this out. Okay. The other problem with it is right now we're just considering kind of charge distributions in free space. We're interested ultimately in, well, what if I've got some sort of conductor here, you know, either a wire or maybe, you know, a conductive plane. You know, how does that affect the D field due to this charge, or maybe multiple surfaces surrounding this thing? So Gauss's law, and this is called the integral form of Gauss's law. And it is useful, can be used in certain simple situations where there's a lot of symmetry, but there's also a differential form of Gauss's law that allows me to develop a differential equation for the D field, which, you know, if I can solve that, you know, if there are other conducting surfaces in the problem, I can apply boundary conditions and hopefully find the D field. So it's actually a fairly easy derivation from the divergence theorem. We had an alternative way to calculate the net flux, right? It says this net flux is equal to the volume integral of the divergence of the D field. But from Gauss's law, this right-hand side is equal to the charge enclosed, which is equal to the volume integral of the charge density over V. Now this has to be true for an arbitrary volume, because again, this is not necessarily a physical volume, but just some shape we can imagine for an arbitrary shape. Then this leads to del dot D is equal to rho V. This is the differential form of Gauss's law. And it doesn't seem to be provide any more information. Remember, del dot D is really a derivative. And it's like if I tell you the derivative of something at a point is 10, you know, that's the slope, but you don't really know what the function is, right? That could be any type of function again. But more generally, we can use this to come up with a differential equation for D. Now, this applies at any point in space. It says that the divergence of D is equal to the charge density at a point. The integral form we have to apply over a region of space. It applies over a volume. Okay, so this applies at any point. So it's also called the point form of Gauss's law. Now, at this point, what we'll be using this for is if I give you the E or D field, you can find the corresponding charge density. Okay. Ultimately, what we want to be able to do is work in the other direction. Given the charge density, can we find the field? But we're not quite there yet. So these are much easier problems. Okay, here's the electric field. D is, let's say this is in free space. D is epsilon 0 E. Del dot D then would be epsilon 0. And remember, del dot D is, that's one of the simple ones. We take the partial derivative with respect to x of the x component of the vector. So the partial derivative of 3x squared with respect to x is going to be 6x. Remember, this is not a vector result. Del dot D gives us a scalar field. And we take the partial derivative with respect to y of the y component. So the partial derivative of xy with respect to y is just x. So plus x. And we get 7x epsilon 0 for the result in this case. So this is the charge distribution in space corresponding to this particular electric field. It says, it depends only on x. At the YZ plane, it's 0. But it says to have this field, our charge distribution actually has to be increasing with x. Now, the one thing you want to be careful with, let's look at another example really quickly. Let's say E is r hat 1 over r squared in free space. And we want to find the corresponding charge density. Well, del dot E, this one you're going to want to refer to this is in spherical coordinates, so refer to your handout, for it's not just the partial with respect to r here. So it's actually the partial with respect to r of r squared times the r component, which is 1 over r squared here. So here we'll have the partial with respect to r of 1, which is 0. So this is 0. So for this particular electric field, the charge density is 0. If you remember, this is actually the electric field of a point charge at the origin. Anywhere else except at the origin, there is no charge. So it's like, if I tell you that the derivative of a function is 0, that doesn't mean the function is 0, right? It just means that the tangent line is 0 at that point, has no slope. That's what's going on here. Having a derivative that's equal to 0 like this doesn't mean that the field is 0. Okay? It just means that there's no free charge at that point in space. But we can still have a field. So again, we haven't talked about how to actually go in the other direction from a charge distribution to the field, but you can use this point form to actually go from the field to find the charge distribution pretty simply. Okay, so we'll talk about voltage and Ohm's law on Monday, some things that you're familiar with. Actually, it's a little easier to solve some of these problems using voltage. And we'll talk about the relationship between voltage and the electric field. Have a good weekend.